All right, hello and welcome everybody to another day in the life of a cloud network engineer at Netflix. Today we're going to be talking about decisions that our team makes on a day-to-day basis. These decisions have been made in the past and we're making these decisions today. And we want to talk about the impact that these decisions have on our team and our company as a whole. Our two main focal areas in this talk are going to be around VPC and DNS. My name is Donovan Fritz. I'm a cloud and network SRE at Netflix.
Hi everyone, my name is Joel Kadama. I'm also a cloud network SRE at Netflix. And I joined Netflix a little over 4 years ago. And when I joined, I was on the corporate network engineering team. And at that point in time, I really had no idea about this AWS cloud thing. I didn't have any interaction with it previous to that. But what I did know is that Netflix had a in AWS. And at the time, this really consisted of Amazon's older environment, EC2 Classic. I know we had some VPCs set up for some testing purposes. And I know from my team's perspective at the time, we managed some VPN connections into those VPCs. And I remember my first real interaction with AWS is when a developer came up to me and he had some trouble connecting to a database. And being the helpful engineer, the fact that I was on call at the time, played into that. But I decided I should help him try to understand these, connectivity problems. So I jumped into the console, figured out what account this was in, figured out what region it was in, did my digging around to find out if this was a network issue. And in the end, it turned out to be a security group problem. Go figure. But what that really told me as an engineer is that in order to be successful at Netflix, I really needed to learn about this AWS VPC thing. So I spent the next several months learning all about VPC, all the components that make it up, right? And you think about, subnets and VGWs and IGWs and CGWs and Direct Connect and route tables and prefix lists and endpoints. I mean, the list goes on of all the things you really need to understand. And for me, it was about mapping those back to the physical constructs that I understood, from a networking perspective. And in all of this learning, I was afforded the opportunity to join a new team that was forming, a cloud network engineering team that was really going to be focused on building a global network infrastructure for the Netflix streaming system. Right? At the time, we were going through a large migration from our classic environment over into VPC. And so, as soon as I was afforded this opportunity, I thought about all the questions that I needed to be able to answer. Like, how does EC2 Classic really work? Right? And what are developers going to take away that the behaviors that need to be moved over from EC2 Classic? And what are the best practices for building VPC? And how does something like our IPC, right, our inter-process communication story play into all of this? Because when building out this architecture, you really have to think about how that ecosystem works. And where do I get started? Right? I'm thinking about building a global architecture. What's the starting point for this? And when you really think about it, you have to start off with kind of the smallest component, which is really, what does an individual VPC look like? But in reality, we needed to compare that to EC2 Classic. For those of you that don't know, EC2 Classic was a very flat network, right? Every single customer shared the same IP space. Every instance was given a public IP address and a private IP address. When you think about this in contrast to VPC, VPCs have this concept of subnets. Right? And subnets really define the kind of IP address an instance is going to get. When you think about private subnets, instances get a private IP address. Public subnets, instances get both a public and a private IP address. And this really plays into how we think about this global network architecture. Now, when I think about private subnets, though, and private IP addresses, one thing that comes to mind from a networking background is, how are we going to translate these addresses? I mean, they need to get out to the internet. We need to provide some kind of address translation. And luckily at the time, Amazon had come out with NAT gateways. Right? NAT gateways are a managed construct to allow address translation. And at Netflix, when we think about leveraging services, we have a common term that we use called undifferentiated heavy lifting. We think about the technical advantages of doing something ourselves. And if we really don't get anything out of it, then we would love to just leverage something that AWS or other vendors provide. And for NAT gateways, that was easy because realistically, they provide a highly scalable and performant service. So we chose to go with NAT gateways in this circumstance. Now, with a single VPC, we could think about moving over all of our classic instances over into VPC, but we really had to consider the fact that we had more than one account in Classic. we had several accounts in Classic. And for each one of those accounts that we were moving over, it needed a VPC. So we really had to start thinking about what was our inter-VPC communication story. Right? How do these communicate to each other? And really, and remember, this is back in 2015 when we were making these decisions on how to build out this global network architecture. When you think about inter-VPC communication, there's really three options available to you. There's the internet, obviously. There's VPC peering, which maintains that traffic within the AWS fabric. And then there's AWS Direct Connect, right? Physical connections into VPC, where traffic would end up traversing through our own data centers or POPs, and then basically go back into AWS constructs. So when we think about this, we have to take all the considerations into play, right? One big thing that we really had to think about, especially because we were using private subnets, was this bidirectional private IP communication. Right? When you think about accounts that need to communicate to each other across these VPCs, we have a mechanism called service discovery. And service discovery is where applications will register to a central repository, and they register with some information. And that information is really their private IP address, and that's how other applications communicate to them. Due to the fact that we're using private subnets, we had to have a mechanism that supported bidirectional private IP communication. And when looking at these, really the internet doesn't provide that. We just talked about using NAT gateways, right, that translate addresses. But VPC peering does, as does Direct Connect.
Joel, when we're creating this type of global architecture, what was the security concerns that we had to think of as well, as if we had this very large flat IP network?
Yeah, when we think about the security story, one thing that we knew that we had to maintain was the ability to use security group references. And what I mean by that is the ability to go into a security group and create a rule that references another security group attached to a different application. Right? This was important for us because our developers were accustomed to doing this. And we wanted to ensure that we could still enable their velocity when we moved into VPC. And when we think about these constructs, the only one that really supported that was VPC peering.
Now, if I remember correctly, when we were making these decisions, we were really concerned about our large clusters as well. We have some really large clusters, and they send a ton of traffic. What do we have to consider there?
Yeah, Donovan, when we were really considering this, we had to think about the fact that we had large applications that were, making large transactions to our data stores, right? When we have Cassandra, we have EV Cache, we have RDS databases. So bandwidth constraints were definitely a concern. And when you really think about this, right, the internet has conceivably unlimited bandwidth when you think about it. When you think about VPC pairing, you're really limited just to node communication. Whatever the bandwidth constraints are from one node to another, that's what you're limited by. Now, at the time, AWS Direct Connect really only supported a single 1 gig interface or a 10 gig interface. And so that didn't really do it for us. When you really think about all these, we made the decision to go with VPC peering. It was a pretty easy decision, and what we ended up with was this full mesh of VPC peers in region. And what this really looks like is it's similar to the EC2 classic environment, right? A very flat network where everything has connectivity to everything else. Now, the challenge here is as we continue to grow and add more VPCs, it's dealing with the complexity of thinking about standardizing this across the board. Now, with that, a little automation goes a long way for that circumstance, and we'll talk a little bit about how we automate that. Now, but one consideration that we have to take into account, which is the ability to have bidirectional IP communication for private IPs. This really carries over when we think about moving this to the global story, right? Because in the global story, we still had services in a single region like Jenkins for integration testing and Bastions for SSH access and users that were sitting in our offices that needed private IP connectivity. And at the time, really, the only thing you could do was set up direct connects and build out your own MPLS backbone to really support this. And that's what we did. So for all the regions we operate in, we went ahead and set up Direct Connect. We then built out fiber ring across all of our regions and extended that to our office buildings. So now we can do service-to-service communication as well as user-to-service communication for those private IPs. Now, the one big thing when thinking about a global network, though, is the IP space you use. For us, we wanted to ensure we had a large enough IP space to grow into, and it didn't conflict with what our offices were already set up with. So we decided to go with the 164/10 or RFC 6598 range. Right? This really gave us the ability to continue to grow and add more regions when we needed to. But And all of that, what this really gives us is a single unified network across all of our accounts and all of our regions and extends to our users to have that connectivity. But in talking to other AWS customers over the last few years, one thing that I've actually noticed is that as we were doing this, it really made our environment very unique. And when you think about kind of uniqueness with our environment, it requires something.
Yeah, absolutely, Joel. So we have a unique global environment where we maintain global IP reachability. And this type of unique environment really demands unique network tooling in order to appropriately manage this environment. So what we've done is we've opted to build our own software to help manage our infrastructure. We've built this in Python, and it's built on top of the Boto 3 SDK. Unfortunately, it's very hyper-specific to not only our company, but also our team. So open sourcing something like this is not really an option for us. So we built a package called CloudNet, and the way this works is it lets us build abstractions on top of the Boto 3 SDK that really help us interact with the environment in the way that we think as humans. So in this particular example, we're creating 2 different VPCs. And these are just one-liners. We specify an account, a region, a name, and a prefix length. So this handles all of the role assumption for us. It allows us to jump into any account that we own, and all that's handled for us under the hoods here. We also don't specify an actual IPv4 CIDR block. We just specify a prefix length. So as Joel mentioned, we have a globally unique address space. So this also hides all the complexities around finding a particular network block to use for a VPC. So it reaches out to our IP address management solution, finds a free network block, and then assigns it to the VPC. So the result here is that we end up with 2 instances of VPC. And then we can just peer them together as well. So again, as Joel mentioned, we have a full mesh of VPC peering. So managing that is really important to us. And so here we can take 2 instances of VPC, just do a .peer2 method, and we pass in another instance of a VPC. And this handles all the heavy lifting, the role assumption to request the VPC peering, accept it, and then it also goes through all the route tables in the VPC and updating the route tables to route the remote VPC CIDR block across the VPC peering connection. It makes management of a full mesh of peerings much more manageable.
I mean, and we can even extend this abstraction to do things new, like resize a VPC. So in this case, we can actually say VPC0.resize. We can, again, just specify that prefix length of a /16. It'll go out and find the right IP block that we're going to utilize. And some of you might be thinking, like, well, all you're doing is adding a new IP block to a VPC. I mean, how hard is that? But it's really everything else that you have to think about, right? That VPC is peered to a whole bunch of other things. And so you actually have to go through every single one of those peerings and update every route table to have reachability. And not only from the routing side, but you have to think about security groups. We have thousands of security groups, and we have to enumerate through every group and every rule and see if we find a match for the existing IP block. And if we do, we have to add a match for the new IP block. Because who wants to troubleshoot something where you have half connectivity? I mean, that's really no fun. And so we ensure that we have this capability across the board, right? And this one-liner does all of that for us.
Yeah, absolutely. And so we've gotten to the point now where we can start building even higher level abstractions on top of that. So we're at the point now where we declare our intention of VPC peerings within this YAML file. And once we create a VPC, we add the VPC ID in here. And we have a pipeline that will kick off, and it will run this single one-liner to standardize our VPC peerings. And this will go through and we'll add any peerings that don't exist. It will true up any that may have deviated from our intent. And it really just makes the complete management of a full mesh of peerings a solved problem for us. I like to say at this point, like moving away from a full mesh of VPC peerings is actually more work for us. And so I think this goes to show really the power of just taking this type of automation in-house and automating it yourself. So you can really get to the point where you understand the interaction with AWS versus trying to understand how to use a tool to interact with AWS. So I think that's one of the key takeaways there. Now, Joel, we've gotten to the point now where we've managed our infrastructure in such a way that it frees up our time to look at more interesting things. What else are we looking at?
Yeah, thanks, Donovan. Now that we have kind of this global architecture, we have the automation to execute upon that, we have to think about other things. Like, how do we integrate new AWS features into our current ecosystem? So for example, last year at reInvent, they introduced this inter-region VPC peering. How many of you are super excited for that to come out? How many of you use it today? All right. Yeah, there's some hands out there. For us, we were very excited as well because we thought this was going to solve some of our, cross-region communication story. And when you really think about it, it would, right? Because now we could do a full mesh of VPC peers in region, and we could do a full mesh of VPC peers across region, and that would solve it. We could think about getting rid of our own MPLS backbone. But when we think about integrating this, there's a couple things we have to consider. First of all is when you consider it to the existing solution, which is AWS Direct Connect, what do we get out of it? Well, one of the nice things is that we do get network-level encryption, right? It comes for free with inter-region VPC pairing. For Direct Connect, we'd have to do that on our own. But that's not our only consideration.
Yeah, absolutely. I think another consideration, if you remember back to when we were just we were going through this decision matrix with in-region VPC peering, we were concerned about these bandwidth requirements of our very large clusters. How does that stack up with cross-region?
Yeah, when you think about the bandwidth constraints, the nice thing is that inter-region VPC peering extends that capability in terms of bandwidth being constrained based on the node that you're using, right? It's node-to-node bandwidth constraint. Now, AWS Direct Connect has evolved over the time, and now you can do things like a 10 by 10 to give you 100 gig of capabilities, but you still have to think about building that out across all of our regions, right? And that's still kind of a management burden, as well as just managing all the interfaces you have to set up for the Direct Connect, all the LOAs and everything there. And that's kind of a management burden, so not great when it comes to Direct Connect in that respect.
All right. I think we're trending in the right direction. What's the security story look like with cross-region VPC peering?
One of the things we were most excited about was this ability to do security group references, right? Can you reference them across region? And unfortunately, you can't, right? And so for us, this is kind of the same across the board. Oh. Mike, hello? Hello?
Hello? Hello?
Oh, there we go. Sorry about that.
Oh, went out again.
I can yell. Can everyone hear me? All right. So we couldn't really do security group references, so neither of these are a real benefit for us.
Yeah, absolutely. So it looks like with inter-region VPC peering, we're definitely a lot better off than we are with Direct Connect. Why not just light it up across the board?
That's a great question. And for us, there was one more consideration that we have to make. And that's really around how VPC peering fundamentally works. You really have to set up a route for every single VPC peer. And when we think about this, right, Direct Connect actually gives us the ability, since we're using this 164/10 IP space, to have one route that represents all of our other regions. And we can set that route in a route table, punt it down to our virtual gateway, and have connectivity across the board to all of our other VPCs in every other region. Hello, I'm back. Maybe?
Nope. Hello?
Hello? All right. So the dilemma here is that when you think about VPC peers, we have to have a route for every single one of those. And we have so many routes in so many peerings in our environment that we fundamentally can't actually do a full mesh of cross-region VPC peers without continuing to push on the limits of our route tables. And when we think about pushing limits, we push limits in all kinds of ways. We not only push them for route tables, we push them for security groups, the number that we can create, the number of rules that we can create. We push them in the number of routes that can be propagated through a VGW, through like Direct Connect. We also push on things like API rate limits. And we not only think about these when integrating AWS features, we also think about these when we're integrating our own in-house features. For example, does anybody here know what Titus is? Oh, a few of you. All right. So to give you a rundown, Titus is our open source container orchestration and runtime platform within Netflix. Right? It's been growing adoption from all of our developers. It runs on Apache Mesos and Docker. And it's been, in its adoption, we're running maybe about 3 million containers a week at this point, right? Quite a few containers. And when we were teaming up with the Titus team to help them solve some of their network problems, right, we had to think about what are those challenges. And one of them is really around an IP per container. When you think about our service discovery we talked about earlier, right? Every instance registers to discovery with its own IP address. And with the containers, we needed the same thing to happen. So from a container perspective, we needed to ensure that we did have an IP per container. And not just for service discovery, but for things like log analysis, as well as some internal tooling. Now, we have an internal tool called Sonar that applies metadata to an IP address, and we wanted to ensure that that metadata was unique for every IP address we were using within our network. The other requirement for Titus and just containers in general is the ability to deploy quickly. Right? That's one of the benefits of containers, is I can build it locally, I can go ahead and ship it up to an AWS instance and have it run very, very quickly. Now, from a networking perspective, this really made us start to change how we view scale inside of AWS. Right? Because traditionally, we always thought about scale in the sheer number of EC2 instances that were running at any given time. Right? Because realistically and generally, an Amazon EC2 instance has one elastic network interface and one IP address. But when we take into account this IP per container solution, right, you now have something like this, where we have IPs that are assigned to containers. All these containers are co-tenanted to an elastic network interface, and all of those are on an Amazon EC2 instance. Right? This makes us think about this paradigm a bit differently, because now it's not scale in the number of EC2 instances, it's scale in the number of IP addresses that are used out there. Now, for the other requirement to be able to deploy quickly, right, we are partnering with the Titus team to think about how do you actually do this? Right? Because there's really a couple different ways that you can slice this, and one of them is doing it on demand. And what I mean is, as a workload comes into Titus, they need to be able to provision everything that's necessary to have that workload running. And this means a whole bunch of AWS API calls. Right? We need to be able to create the network interface. We have to find it and attach it. We have to go ahead and add secondary IP addresses to that, enough to basically sustain all the containers that are needed for that workload. We also then have to modify the network interface to have a security group on there to ensure we have the right security attributes. And really, at this point, we're bounded to the deployment as quickly as we can actually mutate the AWS environment.
All right, so let me think about this. If we can't mutate the AWS network fast enough to deploy our containers, what if we just take a different approach and flip this over and just pre-populate everything up front?
So you're basically wondering if we can populate all of our network interfaces at startup and just like load them up with IP addresses.
Yeah, absolutely.
Yeah, I mean, that seems like a solution. But when you really look at that capability and you think about a growing number of EC2 instances across the board, up to, in this case, 4,000, and we think about the fact that we attach 8 network interfaces to every EC2 instance, and we want to pre-populate those with IPs, I mean, when you really think about the fact that like a VPC is a single/16, then you really can't pre-populate a whole lot of IPs on there.
Joel, you need to think bigger. We talked about earlier how it's super easy for us to resize our VPCs. We need to 5x this, because you can put 5/16s in a VPC.
You're right. You can do 5/16s. And although you can't really assign them perfectly, right, you have to think about breaking them down across all your subnets. I mean, it gives you a little over 300,000 IPs, but when you really think about the rate at which Titus is going ahead and adopting and evolving, I mean, this really doesn't cut it for them. Right? It's just sheerly the number of IP addresses is really not supported. So from the Titus perspective, they had to think about a hybrid model where they really pre-create all of the elastic network interfaces, but they don't actually populate all the IP addresses right up front. They'll do them in batches of 4 IP addresses at a time when workload comes in, and that gives them the ability to kind of sustain this at scale. But one of the things from the networking side is that we still wanted to ensure that they could continue to evolve and grow our network to be able to meet their demand. When Titus first came on board, right, they were an application like any other. They were sitting in our production account, and realistically, they were sitting in the same subnets as all of our other production applications. If you notice here, we actually have 2 subnets because we had run out of IP space to begin with and had to resize once. But there's some concerns about Titus sitting co-tenant with the rest of our EC2 instances. When we think about the co-tenant scenario, one concern is really around IP isolation. When you think about them being in the same subnets as all of our other production applications, realistically, I mean, they're using the same IP pool, which also means that that IP pool could get exhausted. So it's something we have to be really concerned about.
Yeah, absolutely. So I do remember, though, when Titus was first gaining traction internally, that it was super easy for people to move their workloads from EC2 to Titus simply because they could share the security group between their EC2 environment and when they're operating a container.
Yeah, that was a definite advantage here, was the ability to share security groups, right? Because in some cases, we actually have applications that run EC2 instances and Titus at the same time. And so the nice thing here being co-tenant is that you could use that same security group across both of those deployments.
Okay. So is there anything we have to what are we concerned about with the API, right? I mean, we were talking earlier about mutating the Amazon API. What does that look like again in the co-tenant situation?
Yeah, in the co-tenant scenario, you have to think about what this AWS API is. Remember that API rate limits are done at the account level. So anyone sharing that same account, whether you're deployed in the same subnet or not, are actually in contention for all those API calls. So when you think about the ability to create all the network interfaces and mutate them, right, you're really just contending with the rest of our production application, and that's not a great scenario either. And realistically, with the co-tenant scenario, you only get about 98,000 shared IP addresses. And when you think about the size of our fleet and the growing fleet of Titus, and with an IP per container, I mean, that's really not enough.
Yeah, I remember when we were sitting and talking about this problem, we were really in a fortunate situation. You know, we already resized the VPC once, and we always operate in a 3-zone mode in every region, and we can resize 3 more times. So we just went ahead and put a /16 in every zone for them.
Yeah, we gave them their own dedicated subnets, and what that really did is open up the fact that they had IP isolation. They were using their own subnets, so they weren't going to actually exhaust IPs for the rest of our production fleet. They still had this ability to use shared security groups. We didn't solve the AWS API isolation, though, right? Because remember that API rate limits are done at the account level, and we gave them about 200,000 dedicated IP addresses in this scenario.
Yeah, it seems like we're in a better spot than we were originally, but I mean, the next step forward is probably a dedicated VPC.
Yeah, I mean, I think a dedicated VPC might be the natural evolution here, but you end up contending with this shared security group problem. So remember, security groups are bounded to a VPC. So giving them their own dedicated VPC means we can no longer use that same security group if they have applications in EC2, and now they have applications in Titus, or containers in Titus. That's a problem. And it really doesn't solve our AWS API isolation at all. Although it does give them about 100,000 more IPs when you really break it down and assign those to the proper subnets. And I don't think this is really going to fly for them. I think realistically, we have to extend this and go to a dedicated account to give them those AWS API isolations. That way they have their own buckets for rate limiting. But we still have some decisions to make around the shared security group and really how we're going to solve that. But Donovan, we talked a lot about VPC decisions. You were going to talk about DNS. What do we got on the DNS front?
Yeah, absolutely. So again, we spend a lot of our time not only thinking about VPC, but we spend a lot of time thinking about DNS as well. And so within the DNS realm, I want to go back and I want to talk about a really critical decision we made over this past year. And that was around how we use DNS in conjunction with service discovery. So I understand service discovery is a big topic. It can be pretty nuanced and at times maybe controversial, and I don't want to get into all that. But I want to make sure that we're all on the same page. So at Netflix, we use Eureka for service discovery. Eureka is open source. It's on our GitHub page. Anybody's welcome to use it. It's a REST-based service. So anytime an instance comes up, it makes a REST call to register themselves. And as depicted on the screen, when foo wants to be able to discover where bar is, it'll go ahead and make a REST request to get a list of nodes in which bar is operating on, and they're off to the races. Now, the nice thing about Eureka is that it has this concept of states that EC2 clusters can be in. So we frequently red-black our clusters, or as some people call it, blue-green. And Eureka has the ability to just flip that state of clusters in very quickly from in-service to out-of-service. The whole time, foo is able to satisfy its request and be able to figure out the current in-service version of bar. Now, the frequent question that we've had for a long time, and it predates my time at Netflix, is how can we use DNS? We don't want to use a REST client. We're using a web browser. I want to be able to just type in a host name. And so to solve this problem, what we've done historically is we've just synchronized all this data into a Route 53 public hosted zone. So by using a common naming format, we send and synchronize the state that Eureka has in terms of what's in service and out of service in the world, and we create records inside Route 53 to solve this DNS requirement. Now, over time, this has become problematic. We're now at a state where our environment has become large enough that this synchronization process is a problem. We have a ton of more microservices. We have a lot of changes, especially with Titus. IPs coming and going all the time. We're simply at this spot where we can't mutate a Route 53 public hosted zone fast enough. And so again, we're at a critical decision where we want to figure out what we can do in this situation. Now, our team doesn't manage Eureka internally, but we like partnering with other teams, and we sat down with the team that manages it, and we got together and we tried to figure out what can we do about this problem. So anytime we want to make a decision and try and move forward, I think it's helpful to go back to a decision matrix and figure out what are we actually trying to solve for. So in this particular case, our existing solution does a great job at auto-removing stale DNS records. It also has the great in-service, out-of-service capability that we've come to know and love. But again, the problem is we simply can't mutate the Route 53 public hosted zone fast enough.
You know, Donovan,
yeah.
I talked to AWS about this.
Okay.
As we often do to figure out if there's any solutions we can use out there. And they said, let's look at this route, this auto-naming service, the Route 53 auto-naming. And it does something very similar where it'll create DNS records for instances that are coming up. But when you really stack this up to kind of the criteria here, it doesn't remove auto-stale DNS records. So we would still have to kind of do that on our own.
Okay.
And it doesn't know anything about our own internal discovery. So out of service would have to be our own hook. Now, being an AWS service, though, it has its own rate limits. So the benefit there is that, those rate limits are much higher than what we as a customer have. But in the end, I just don't think that I don't think it's going to fly.
Yeah, unfortunately, we're not always able to leverage an Amazon service the way that we'd like to. And in this particular case, this is a problem that we're currently experiencing, and it's actually impacting some of our internal applications. And people are coming to us, the on-call people, the team that is supposed to be the managers of DNS at Netflix, and they're having these problems, and we really need to solve this today. And so what we did is we thought of, hey, we can build something in-house to solve this problem. So we created a DNS layer on top of Eureka, aptly named Eureka DNS. This is a little bit laggy. The clicker's not working? Let's go forward, yeah. Okay, we'll just go here. So historically what we've done is, again, we synchronize this into a Route 53 public hosted zone. So our thoughts in what we did in this scenario was we simply swapped that Route 53 hosted zone to a set of authoritative name servers that we own and operate. So in this particular case, it doesn't really matter who's servicing the DNS request. DNS is your contract, and as long as you're satisfying that contract, you can really operate any sort of authoritative name server you want. So in this particular case, we no longer have an actual common DNS zone that you would typically think of. We're simply taking a DNS request and we're synthesizing the response based on data that we have in Eureka at that point in time.
Wait, Donovan, you're telling me that we're going to build our own authoritative DNS servers in AWS?
I'm not telling you that we're going to. I'm telling you that we did.
All right, all right.
Okay, so anytime, and that's the great thing about EC2 is you can really build whatever you want. But for something like an authoritative name server inside of EC2, you need to just think about what it actually takes to accomplish your task. And so we go back to our decision matrix again, like what do we need for an authoritative name server? We need static IPs. We need IPv4 support. We need IPv6 support. And obviously DNS is UDP, so we need UDP support.
All right, I got it. How about we use network load balancers to be able to service this?
The NLB was released at AWS last year. So let's think about this. An NLB supports static IPv4 addresses. They're static. But it comes up a little short on the v6 story, and obviously no UDP support, so that's a clear non-starter.
Yes, if only they supported UDP. Okay.
If only.
What about an elastic IP address? I think an elastic IP will work.
Okay, an elastic IP. So an elastic IP, it assigns directly to an instance. I'd call it a primitive. And since you assign it to an EC2 instance, you can operate whatever IP protocol you want through it. But by definition, they don't support IPv6. And hold on, before you say it, I'm not going to let us do something without supporting IPv6.
Okay, you and the IPv6. All right, let's see. I like the elastic IP, though. But what if we just create an elastic network interface? We assign that elastic IP to it, and then you can have your IPv6 address.
All right, I think that'll work. So now we can attach this to an EC2 instance. So we can operate whatever IP protocol we want. We get both V6 and V4 support. And I think we have a winner.
Yeah, but what about the high availability story? I mean, it's a bit of a challenge, right, to use a single elastic network interface.
Yeah, we definitely have to take a little bit more care in how we actually deploy this internally, right? So let's think about how we do this. So what we've done is we've gone ahead and pre-created all these static ENIs. The static ENI will have V4 address, V6 address, and it'll have the appropriate security group to allow UDP traffic in. And so now when we deploy an EC2 instance, it'll go through a discovery process. And then in that discovery process, it finds the ENI, attaches itself to it, and then it's able to service DNS requests that come into that IP. So we also have to consider how we essentially red-black a DNS cluster, because that's how we deploy updates. In this particular case, a new instance comes up, it discovers that ENI, moves over to the new instance, and then the old one goes away. Old one goes away. And at this point, we've deployed an update to a DNS cluster. It's pretty cool. Now that's just one little building block. We also have to consider how we do this because at a larger scale, because again, we don't just delegate a DNS zone to a single IP. We have to do this multiple times. So what we've done is we've replicated that particular setup we just talked through twice per availability zone, and then again, we always operate in regions that have 3 zones, so we just replicate it again out for every zone. In addition to that, we have to then take that template and stamp it out across every region that we operate in, and then again per different environment. So when I'm talking about environment, I'm thinking testing and production. So we end up with this cookie cutter scenario that we just replicate out multiple times. And one of the really cool things about this is that your DNS namespace gets very, very well structured, and something that I like to call a DNS delegation hierarchy. So in how we actually ended up deploying this is we take our 3rd level domain, eureka.netflix.net in this case, we delegate out our environments, and then from there, we delegate our regions. So now, as an application developer at Netflix, if you simply deploy a service and use the Netflix ecosystem, you'll get a host name for your service. And so the great thing, again, about this is that it's really rigidly structured in terms of your namespace for your DNS hostname. And I think that's another really powerful concept that anybody can use, even if you're not doing exactly what we're doing here. If you take care with your DNS namespace and you structure it, and you don't have to structure it exactly like this, but if you put enough foresight into there to structure it, you end up in a really cool scenario. So now for us, what we can do is we can flip between different stacks of our deployments. So you can simply change the region name and the host name to go from one region to another. You can check out your test and your prod versions by simply changing a token in the host name. It's really cool.
Yeah, Donovan, this is a very interesting solution to a problem we had. But one theme I'm seeing with all of these things is that we're being very reactionary to things that we're dealing with, right? Problems we're coming up against. Isn't there a chance for us to be a little bit more proactive in some things we're working on?
Absolutely. So as we talked earlier, we've kind of fought a bunch of fires already, and we have a lot of automation and tooling that helps make our day-to-day operational workload super easy. And it kind of frees us up to be able to think more proactively about things that we want to work on. And within DNS, there's definitely an opportunity to do that. And what we've identified for an opportunity is around DNS steering. So when any one of our 137 million users around the world open up their web browser and they want to watch Netflix, they type www.netflix.com. And we have to, at the DNS level, steer them to one of our 3 regions that we operate in. Now, from a serviceability perspective, it doesn't really matter what region we send you to, because on the back end, we replicate all your bookmarks, your profile, all that good stuff across all 3 regions, so we can service any customer from any region. What we've done historically, though, to solve this problem is we've used geography. So GeoDNS, as it's commonly referred to, we have a static hand-tuned policy where we map particular geographies of the world to our AWS region, and we're off to the races to kind of solve this problem. So a user in San Francisco, for example, would be statically mapped to our US West 2 region, and a user in London would be statically mapped to our EU West 1 region. And this ends up having a big impact on how each region's receive, the traffic that they receive from our customers. So what we're looking at here is a request rate per region as a percentage of our global request rate. And each region is broken out to their own color. We have the percentage of requests on the left-hand side, and this is over time, and we're looking at a one-week time span. Now, if we did load balancing with GeoDNS perfectly, or just DNS in general perfectly, we would end up with this perfect balance at 1/3. So in theory, the best we could ever do is 1/3 distribution between our 3 regions. And so we call anything above that 1/3 boundary an availability risk. And so in the event of a regional failure, if we have to evacuate a region, if we're moving more than 1/3 of our customers, we're being more risky with our customers' traffic than we really need to be. Right? So, and then once we're failed out of that region, we should be having a perfect balance at 50% for our 2 regions. And so we consider anything above the 50% threshold a cost driver. Because again, we're able to fail out of any region at any time. In order to accomplish that, we need to maintain EC2 instance capacity in every region to support any other region's failure. So we're at a point now where we're thinking, we can do one better here. We can definitely optimize our cost driver and our availability risk simply by being a lot smarter with how we resolve DNS for our customers.
Donovan.
Yes.
Again, I talked to AWS about this, looked at some available solutions, and we said, okay, well, we're not really optimizing for latency. What if we optimize for latency? What would that actually look like?
Okay.
Right? So what if we utilize Amazon's Route 53 latency-based routing? Right? When you think about latency-based routing, it really takes that other pillar into concern, which is performance. So if a user, when they make that DNS resolution, they're going to look at their latency to all the regions, and they're going to send them to the region that has the lowest latency. And so similarly, like Geo, when you think about like a user in San Francisco, they're going to go to US West 2. You think about a user in London, is going to go to EUS 1. And as we started considering this, we thought, well, how do we really understand what the ramifications of this are if we chose to go fully with latency-based routing across the globe? And so in order to get that data, we instrumented these real user measurements. And real user measurements are basically probes that go out to every single region and identify what the latency is to every region from our clients. And so there's a very small percentage of chance that those of you out there, when you open up Netflix on your devices, you're sending these probes. And then you're sending all that data back to us so that we can go ahead and do things like model out what it would look like if we chose everyone's region based on the lowest performance or the lowest latency to that region. And really, this is what it ends up looking like. If you notice here, it ends up being a very large skew. And there's one region that sticks out in particular that has now roughly 75% of our client requests during peak. And that region is US East 1. And the concern here is that we're really not trending in the right direction, because now we have this much larger availability risk. We actually have this much larger cost driver. And for us, we were trying to drive that down. So really, latency-based routing wasn't going to do it for us. And I mean, when you look at that US East 1 and how much percentage of client requests there, I mean, Donovan, why would something like that actually happen?
Yeah, it's a good question. So maybe let's go through a little mini case study and to try and figure out and understand how we ended up in this scenario with latency-based routing. So we'll look at a map of the world, and we'll put 3 users in the world. So we have a user with our yellow dot in the Midwest of the United States. It looks like it's in Wisconsin. We have a user with the blue dot in Spain. And then we have a user way down in South America in Argentina, it looks like. So the user in yellow has great connectivity to the 2 American regions, and then decent connectivity as it goes across the Atlantic over to our EU region. The user in Spain obviously has great connectivity to our EU region, slightly more latent as you go across our 3 other regions in America. And then the user in South America, since we don't operate in that region, we have to bring that traffic all the way up to North America or Europe, and that added distance adds network latency here. So every user's preferred region in this particular scenario, we end up with a 2/3 distribution to US East 1. Now, if we transcribe this data onto a table, it's a little bit easier to see. Again, we see the 2/3 distribution to US East 1. Now, again, we didn't have this problem with GeoDNS. If you remember, it was much differently balanced. So the way that GeoDNS worked for us is we had this hand-tuned static policy where we mapped a particular geography to a region. In this particular case, we achieved better balance by mapping Wisconsin to US West 2. Now, GeoDNS is interesting when you really start to dig in and figure out how it works from a technical perspective. Fundamentally, it's an authoritative name server, and it gets a DNS request. It looks up the source IP in this thing called the geo database, And then it derives the geography from where that request came in. And then it has to look at our geo-steering policy map that we gave them and figure out how it should resolve our particular DNS request for us.
You know, Donovan, if we want to fix this, I think what we need to do is be more granular in how we have the ability to control where, what prefix goes where. So why don't we just cut out that geo and we just build a prefix map based on those prefixes directly?
Yeah, absolutely. So this is where we're trending, right? Is we're exploring this idea of if we just cut out the geo layer and instead just do everything based on prefix, we could, in theory, get much more granular on what we're trying to accomplish here with our DNS steering. So now, instead of a geography, we have IP networks. So we're sending an IP network to a particular location. And one of the other things that we thought of when we were going through this process is that, every so often we actually do regional failures proactively to prove to ourselves that we can, in fact, sustain any region going down. We call these Kong exercises. So whenever we run a Kong exercise, we'll completely take down an AWS region and we'll serve everything from 2 regions. And in those scenarios, we actually are adding latency to customers' requests that may be going from an optimal region to a slightly more latent region. And what we've learned is that these customers actually don't notice a difference. It's imperceivable to them. They have no impact to their experience. And so we came up with this idea of there's a threshold where we can actually add a little bit of latency to our users' requests, and it's imperceivable to them. We call it an imperceivable impact. And so in this particular example, we're using 100 milliseconds as example. And if we, in theory, were to have this delta where we can add we have a little bit of budget to a particular user's request, it really opens up the world in terms of options for steering. So now the prefix in yellow, if they have sufficient network connectivity, they can really be served from any region that we operate in. And the prefix in red is similar, where not every region, but there's 2 regions that really stick out where they should be steered to. And the user in blue is similar, but at 2 different regions. And so at this point, we've essentially turned DNS steering into a big data problem. We have every prefix on the internet and tons of data points, and we're trying to figure out what is the optimal steering policy to optimize for our cost, availability risk, as well as latency. So we went ahead and we actually probed this out using the same real user measurements that Joel was mentioning earlier, and this is what we ended up with. Now, you can see that we're getting much closer to that perfect balance. I don't think we'll ever be able to achieve it, but you can see that we've reduced our cost driver, and we're getting really close to that perfect balance. Now, if we map out geo-steering on a map of North America, this is kind of what we ended up with. We can see clear geographic boundaries where, for example, Mexico is being steered to US East 1 in white, and the vast majority of the United States is going to US West 2 in red. Now, if we take the same map and we plot our prefix steering, it becomes way crazy, right? There's no geographic boundaries being observed here. And in fact, we see another color. We start to see blue. And this is representative of customers in North America that have sufficient network connectivity that will notice no impact will have no impact to their experience if we were to, in fact, steer them to EU West 1 via DNS. So now we're at a decision point. We haven't made this decision. We're still exploring it. And we want to figure out what we can do with this data. We would love to be in a situation where we could simply provide this type of data set to Route 53 and have them operate the authoritative name servers and have the contract, the data that we send to them, such that they would respond to our DNS requests based on what we provide with this data. If these decisions are interesting to you, we would love to talk to you. We love talking to companies about just about anything. At our hearts, we're nerds, we're geeks. And if these decisions are interesting to you, again, come talk to us. We have openings on our team, and we would love to add more stunning colleagues as well.
Thanks, everyone, for joining us and hearing a little bit about what we deal with on a day-to-day basis on the cloud network engineering team. Thanks for listening to our story. And we do have an expo booth in the expo hall. So unfortunately, it's not open right after this, but we'll be there throughout the week. So if you want to stop by, come and talk to us. Our contact's up there. And if you guys have any questions, we can answer some questions over here. We have a few minutes before the next session. But thanks, everyone, for joining. Please make sure to rate us. Thanks, everyone.
Thank you.